It's the practice makeup exam, part 2. In this problem, we have to find the molecular geometry of the cation BrF4+. So first, we need to draw a Lewis structure, and to do that, we need to know the valence electrons. Now, both bromine and fluorine are in group 7, so each of them brings 7 valence electrons to the table. So we've got 7 from bromine. We've got 7 times 4 coming from the fluorine, because there's 4 of them. So that would give us 35, but because it is a cation with a positive 1 charge, we're going to subtract 1 from that, and we're going to get that there's a total of 34 valence electrons. From that, we're going to now draw the skeleton of our Lewis structure. We have a bromine in the middle, because it's the least electronegative of those elements. We'll put a fluorine on, fluorine, fluorine, fluorine. Okay, so we've got 4 bonds depicted, which is a total of 8 valence electrons. We've got 34 that we need to place. So recall now that what we're going to do is put electrons on the outermost atoms until they have an octet. And if we have any left over, we'll put them on the bromine. So let's do it. We've got 8 accounted for. 9, 10, 11, 12, 13, 14. Octet achieved. 15, 16, 17, 18, 19, 20. Octet achieved. 21, 22, 23, 24, 25, 26. But wait, there's more. 27, 28, 29, 30, 31, 32. So we've got 32 in there, but we've got 1 more lone pair that we need to account for. So I'm going to put that on the central bromine, which is perfectly fine by bromine because bromine is a large atom. It's got the real estate available to expand its valence shell. So in order to figure out the molecular geometry, we need to consider the electron domain geometry first. That's going to dictate what shapes are possible. There are 5 electron domains, and recall that the way to get 5 electron domains as far away from each other as possible is through this shape where we have these 3 electron domains in the same plane as each other, and then we have 2 electron domains that go above and below that plane. So this shape here, because we have that trigonal plane in the middle, and then we have these 2 points above and below, this ends up being a shape called trigonal bipyramidal. We have a trigonal bipyramidal electron domain geometry, but we're looking for the actual molecular geometry. So we're going to consider the shape, and then what we're going to do is just make one of these a non-bonding pair. And whenever you have 5 electron domains, you always start with those trigonal planar ones first, the ones that are equatorial, before you start putting lone pairs on the axial ones. So we end up with this shape, arguably the most fun shape in all of chemistry. The molecular geometry here is the the seesaw. Okay, so our overall molecular geometry ends up being the shape which kind of looks like a sideways seesaw. And just for posterity's sake, I'll throw in the lone pair of electrons here. So our answer is A. This question says, what type of hydrocarbon chain do we have, and what functional group is present at the end? So we've got this double bond all by its lonesome out here. So we're looking at an alkene. And in terms of the functional group, so over here at the end of our molecule, we have this double bonded oxygen, a carbonyl group. But remember, there's also secretly something happening here that's not depicted. We have our hydrogen friend named Al. I'm Al. Why is his name Al? Well, when we draw the skeletal structure, we don't have to depict him. Why not? Well, because it's assumed that hydrogen is bonded to that carbon. So what happened? Aldehyde. Zing! So we have ourselves an aldehyde functional group. We have a carbonyl, and that carbon is attached to a hydrogen. So it is going to be an alkene with an aldehyde. In this problem, we have to figure out the bond order of the carbon-oxygen bond in carbonate. So first we need a Lewis structure. And that Lewis structure, so let's see, we've got 4 valence electrons from carbon. We've got 3 oxygens, each of which bring 6. And because it has a -2 charge, we're going to have to add 2 more electrons, which gives us a total of 24 valence electrons. Okay, so now we're going to draw our skeleton for our carbonate. We're going to put carbon in the middle. And then we're going to draw an oxygen here, and an oxygen here, and an oxygen here. And now we're going to put in our lone pairs to make sure everything on the outside has an octet. So we've got 1, 2, 3, 4, 5, 6, 7, 8 electrons there. We're going to give this one an octet as well. We're going to give this one an octet as well. And when we do that, we'll end up seeing that we've used up all of our electrons. So now we end up having our total of 24 electrons drawn in, but carbon here, well, this carbon is not a happy carbon. It's a sad carbon, because it doesn't have an octet. So it's going to need to have an oxygen share. So which oxygen would be most advantageous? This one, or this one? Trick question. It can be either of those. So I'm just going to make it from this one up here. I'm going to move one of those lone pairs and create a double bond. But that's not the only way that this could be done. We also could have drawn this structure with a double bond put right here instead. Or if we want to be particularly saucy, we could instead do it here instead. So this is an example of a situation where we have these 3 equivalent resonance structures. So it's not like we've got 2 single bonds and 1 double bond that are just alternating positions. No, we need to consider the bond order, which means we need to take the average taken across all 3 of these structures. So our bond order here, we're going to pick our favorite carbon-oxygen bond. Doesn't matter which one, I'm just going to go with the top one. So we have to count the total number of bonds on a particular carbon-oxygen connection. So we've got 4 bonds, and those are distributed across 3 different structures. So we're going to divide this by the number of structures, and that's going to give us our bond order of 1.33. Okay, in this problem we're trying to find which of these interactions would have the highest energy. So these are interactions of point charge, so we're going to use our definition for our equation for electrostatic potential energy. It's equal to the proportionation constant K times the charge on point charge 1 times the charge on point charge 2 divided by the distance between those 2 point charges. So we can narrow down our answers a little bit by considering if the charges are like or unlike. Whenever you have like charges, so for example, a positive and a positive charge, or a negative and a negative charge, a positive times a positive and a negative times a negative will always equal a positive value. So that means that the greater, or if we have like charges, we're going to end up with a positive electrostatic potential energy. Remember that corresponds to repulsion here. Lower energy is more stable. So if we have unlike charges, like a positive and a negative, or a negative and a positive, then we're going to end up having a negative energy, a favorable stabilizing interaction. So we can eliminate all the choices that have unlike charges because those are going to be negative in energy, and we're trying to find which one has the highest energy, the most positive. So we can eliminate choice B right off the bat. We can eliminate choice C right off the bat, and that's about it. Now between these next 3, they're all like charges, which means they're all going to correspond to repulsion, and we don't have to actually calculate the number itself. We can calculate these in charge or in terms of how they relate to the proportionality constant K divided by a distance. So what I mean by that is we just need to get these in like terms. So for A is going to be equal to, using this equation up here, the charge on point charge 1, which is positive 1, times the charge on point charge 2, which is also positive 1, times K divided by D. So if we put these in terms of K over D, we end up getting the following. We get 1 KD. Okay, so we're going to do this now for choices D and E and see which one has the greatest magnitude. So it's going to be K times the charge on point charge 1, positive 1, times the charge on point charge 2, which is positive 3. And the distance now is doubled. So it's going to be times 2d, which ends up giving us 3/2 kd. Okay, so now we have a new winner. This one is 1.5 times kd. But let's take a look at this last one. This one has the same magnitude of charges as choice D, except these charges are a lot closer, so they're going to be repelling each other a lot more and have a higher energy. To quantify it, this is going to end up being 3 times 1 times k over d, which gives us 3kd. So this one is positive, and it is the greatest magnitude of the 3 possible choices. This question wants to know what type of intermolecular forces there are in a molecule of BF3. So BF3 is an interesting molecule. If we look at the Lewis structure of it, it looks like this. So we've got a boron in the middle, we've got 3 fluorines around it, and fluorines don't tend to make any multiple bonds, although scientific studies show that there is a little bit of resonance character in this molecule, so there is a little bit of a double bond character, but this is the primary structure that describes this. Regardless, it doesn't matter, because if we look at this shape, it ends up being, so we have a polarized bond here, we have a polarized bond here, and we have a polarized bond here. When it's all said and done, they all cancel out, so there is no net dipole in this molecule. So LDFs are a given. Everything has got LDFs. But there is no dipole, so it will not have dipole-dipole interactions. Furthermore, we don't have hydrogen bonded to a nitrogen, oxygen, or fluorine. So there's not going to be any hydrogen bonding. So the only type of intermolecular forces this has available are LDFs. This question tasks us with finding the wavelength of light necessary to excite an electron from n equals 1 to n equals 4 in the hydrogen atom. So if we're looking at electron transitions in hydrogen, we can use the Rydberg equation. So here is our equation. The change in energy for an electron transition in hydrogen is equal to a Rydberg times 1 divided by the initial quantum state squared minus 1 divided by the final quantum state squared. So we want to find out the energy change that this is going to take. And we're going from a lower energy, which is more stable, to a higher energy, which is less stable. That's going to require energy to go in. So our value should be positive, and indeed it will be. So let's plug in our values. We have delta E is equal to a Rydberg, which is 2.18 times 10 to the negative 18th joules, 1 divided by n sub I squared, which is 1 squared, minus, and it's going up to n equals 4. And when it's all said and done, we'll end up getting 2.04 times 10 to the negative 18th joules. That's the amount of energy it's going to take to promote that electron from n equals 1 to n equals 4. Now, we're not looking for the number of joules, though. We're looking for the energy that it corresponds to. So recall that the energy that relates energy and wavelength is E equals hc divided by lambda. So we used this equation previously. This time we have the energy, and we're going to be solving for lambda. So let's plug in what we know. So here we have everything plugged in, and now what we're going to do is multiply both sides by lambda. And then we're going to divide both sides by our energy. We'll end up getting that lambda is equal to 9.75 times 10 to the negative 8 meters. Since all the answers are in nanometers, recall that for every 1 nanometer, nano means 1 times 10 to the negative 9th meters. So when doing our conversion, we'll end up getting that lambda is equal to 97.5 nanometers. For this question, we need to figure out what orbitals overlap to make this bond here. So this is a skeletal structure, which means we're not seeing the full picture. First of all, nitrogen. We can assume that all these things have octets unless otherwise noted. So nitrogen has a lone pair that's not drawn in. And also, that carbon has a sneaky hydrogen That's not drawn in. So to find the overlapping orbitals that make these, we have a single bond which consists of one sigma and one pi bond. So in order to find what's making the sigma bond, we need to look for the hybridization on both this atom and this atom. And to do that, we're going to use our friend, the SPPPDD rule. So we count the number of electron domains, and then we count over. And in both of these cases, so if we look at both of these, they each have 1, 2, 3 electron domains, 3 branches of electrons. So that's for the carbon, and it's the same story for the nitrogen, 1, 2, 3 electron domains. So that means that if we look at the hybridization, we're going to count over 1, 2, 3. Each of these is sp2 hybridized. So each of our atoms is sp2 hybridized, which means that our sigma bond is created from this overlap of those hybridized orbitals. So it's an sp2 overlap. But since it's a double bond, that means there's also a pi bond involved. Pi bonds will always just be p orbital. Both of these have one unhybridized p orbital that's not being invoked. In the sigma bond, it's what's used to create the pi bond. So our answer is going to be sp2, and pp. The next question says how many sigma bonds and how many pi bonds are present in caffeine. So the pi bonds are going to be a little bit easier to count. I'm going to we're going to enhance and make this larger to make it a little bit easier to see. Aha, there we go. Now we're going to go through and we're going to count all the sigma and all the pi bonds. I'm going to start with the pi bonds. So pi bonds, every double bond has one pi bond. Every triple bond has two pi bonds. It's the most delicious bond of all. And I'm just going to tally them off. We've got 1 here, 2, 3, and 4. So there are 4 pi bonds. Okay, but now for the sigma bonds. Every bond, be it single, double, or triple, has a sigma bond. So we need to remember that these skeletal structures don't necessarily show us the hydrogens. There is that one sneaky hydrogen right here. And what I like to do in order to answer something like this is I like to go through and I like to tally up to see how many sigma bonds there are total. I just like to cross them off as I go through. So that's what I'm going to do here. If it helps, you can try drawing out, for example, if instead we wanted to visualize all the bonds, we could kind of cross this out and we could draw out all the individual bonds on the CH3. Sometimes this is helpful when tallying. So I'm going to go through and tally up all the sigma bonds. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. By tallying off like this, you can make sure that you're not missing anything. So we've got 4 pi bonds and 25 sigma bonds. In this next problem, we have 2 entities. We have a gas canister, and our gas canister here is a cool 3 liters in size, and it's charged to 5 atmospheres of pressure, and it's going to be connected to some sort of bizarre shaped container. So I'm going to make my bizarre shaped container, let's make it like a wild, wacky, inflatable arm-filling tube man. One of those things that you can get to advertise like a used car dealership. So, because this is an irregular shape, it would be very difficult to do this through a traditional geometrical approach, but by using the power of gas laws, we can figure out the volume of this. So we're going to use the relationship P1V1 equals P2V2. So initially our gas starts just in here. So we have gas that's in here. And initially, it takes up a volume of 3 liters. So we have a pressure of 5 atmospheres, and we have a volume of 3 liters. Okay, so then when the partition is removed and the gas is allowed to diffuse through, so it spreads out and it occupies that entire space. It tells us then that after this, the new pressure is measured to be 1.75 atmospheres, which means we can find the total volume of our container and our wacky shaped container. So we end up getting that the total volume is 8.57 liters. Now that is the volume of all of this, including our initial gas canister. We want to know what is the volume of only the weird shaped container, which means we need to subtract the 3 liters from here. So the volume of our container will be equal to the 8.57 liters minus the 3 liters from our container, which ends up giving us 5.75 liters. This question says, which of the following types of light has the highest frequency? Highest frequency. What are we talking about here? So remember that in terms of frequency, higher frequency means higher energy, which means a shorter wavelength. So I'm going to put the entire electromagnetic spectrum up here, and we're going to see which one of these wins. So let's start with the visible part of the spectrum. So our visible portion of the spectrum, we can use the mnemonic Roy G. Biv to figure out. And if we consider this, in the words of the poet and philosopher John Bon Jovi, whoa, we're 7/13 of the way there. So there's 6 more types of light that we do not have indicated. In order to think about them, think about what comes beyond red. So beyond red is infrared. So it's past red. What comes beyond violet? Well, if it's not regular violet, it's ultraviolet, UV. Now we only need 4 more to complete our spectrum. So if we want to consider which side is higher in energy and which side is lower in energy, think about these 2 different types of light, infrared versus ultraviolet. Which type is it that can do damage to skin cells on a bright sunny day? Well, it's going to be the ultraviolet. So this side of the spectrum corresponds to higher energy, which means higher frequency, which means shorter wavelength. Whereas on the other side, we have lower energy, we have lower frequency, and we have longer wavelength. All right, so past ultraviolet are X-rays, and even higher than that are gamma radiation. On the other side, past infrared, we have microwaves, and then we have the lowest energy wave of them all, which are radio waves. Now we've got the entire spectrum here. We're trying to find the highest frequency, which means the highest energy. And of these, the one that has the highest energy is going to be blue. Blue is higher in energy than green, red, infrared, and microwaves. This question asks which of the following phase changes are exothermic. So let's just quickly go through all the phase changes. So solid, liquid, gas, and let's talk about which phase changes are endothermic and which are exothermic. So our endothermic processes, the ones with a positive delta H, are going to be the ones where our matter needs to absorb heat in order to do it. So to go from a solid to a liquid, we need to add in heat. This process is called melting. to go from a liquid to a gas. This is called boiling, or evaporation, or vaporization. That one's endothermic. And then finally, we have a solid directly to a gas, which is sublimation. All of these phase changes are endothermic. On the flip side, we have the exothermic ones. So let's just quickly go through which ones have a negative delta H and are exothermic. So those are going to be, if we go from a gas to a liquid, which is condensation, liquid to a solid, which is freezing, and then finally if we go from a gas to a solid, that's called deposition. So we're looking for the exothermic ones here. So let's fill in what each region of our phase change diagram corresponds to. We have solids here, we have liquids here, we have gases here, and we're looking for any of these phase changes. So we're looking for going from a gas to a liquid to a solid, or a gas to a solid. So the ones that correspond to that are, we've got a gas to a liquid. So right here we have condensation. Here we have freezing, going from a liquid to a solid. And all the other ones are endothermic. So it looks like it's just 2 and 5 only. And my apologies, I evidently didn't put in a correct answer. So let's go with choice F, which is 2 and 5 only. Sorry about that. This one wants to know what the proper formula for the salt between barium and oxygen would be. So we need to consider the charges. Barium is in group 2. It's got 2 valence electrons, so it'll lose them to become positive 2 in a salt. Then oxygen is in group 6, so it will gain 2 electrons when forming a salt to have its octet. So we have a -2 charge and a +2 charge. Since these are even in charge, it's a 1-to-1 ratio, which means we only need 1 barium for every oxygen. So barium oxide is BaO, B-A-O. In this question, we have a system undergoing some changes. I really like to use a little diagram for these types of problems, where I'm going to label this the system. And we're going to consider all 4 of these different energy exchanges, and then we're going to see what the overall energy change is. So whenever we have a process where we're either contracting the system, performing work on it, or it's absorbing heat, we're going to draw an arrow toward our system. So that's going to be energy in. And whenever we have it releasing heat or doing work on the surroundings, we're going to put an arrow that way. This is going to be energy out. Okay, so with that in mind, let's go through and tally up all these different energy changes. So first we have the system absorbs 5 kilojoules of heat. So if it's absorbing heat, we're going to put our arrow like this. And I'm just going to label this 5 kilojoules. Okay, up next we have the system has 50 joules of work performed onto it. So if the work is being performed onto it, we're contracting our system here. And we want to make sure that our units are consistent. So this is 500 joules, which is 0.5 kilojoules. Okay. Up next, it says the surroundings absorb 1.5 kilojoules of heat. So if the surroundings are absorbing the heat, that heat has to come from somewhere. It's going to come from our system. So it's going to be giving off. And whenever we have the arrow pointing outward, our sign is going to be negative. So now it's going to be negative 1.5 kilojoules because this heat is being lost from the system. So negative 1.5 kilojoules, which leads us to the system releases 1 kilojoule of heat. So once again, we're going to draw our arrow going out this way, and it's going to be -1 kilojoule. And now what we're going to do is just add together all of these values, and we'll get the total energy change. The overall delta E is the sum of all of these, which ends up being positive 3.0 kilojoules. So there is a net increase in energy of the system. This question says how many unpaired electrons are in a vanadium 2+ ion. So the first thing we're going to do is write out the electron configuration of vanadium, neutral vanadium. So vanadium, neutral, because whenever we want to do this for a cation, it's always prudent to write out the neutral electron configuration first. Neutral vanadium has an argon core, then it's 4s2, and then it goes into the D block. We're looking at a transition metal here, so 3d3. It's the third element in the D block on the fourth period of the periodic table. So then when we want to make this vanadium 2+, recall that when we're looking at a transition metal and we're trying to make it a cation, we always take from the furthest out shell first. The 4s we're going to take first. So we need to remove 2 electrons, which means those 4s are donezo, and we're left with only 3d3. Okay, so now finally it asks how many unpaired electrons are there. So we only have, core electrons will always be paired up. So we don't have to worry about figuring out any unpaired electrons from there. In a D subshell, how many orbitals are there? There's 1, 2, 3, 4, 5. And if we want to number them, we can give these m sub l values if we wanted to. So -2, it's not necessary in this problem. I'm just doing this for posterity's sake. And then finally, we're going to tally up the total number of electrons. And remember, when we fill out our electrons, we're going to put in 1 per orbital at a time. So 1, 2, 3, and we're done. And none of them are paired, so the answer is just 3. This next question asks what are the quantum numbers that describe the highest energy electrons in an orbital of iron 3+, or in the highest energy orbital. So once again, we're going to start by looking at our neutral ion. Iron is the 6th element in the 3D block. So it has an electron configuration, neutral ion that is, of 4s2 and then 3d6. Since we're looking at iron 3+, though, that means that we're going to need to remove some electrons. Which electrons are we going to remove? Well, we always start by removing the 4s electrons before the 3d ones, which gives us 3d5. So we took both of these electrons and we took one of these electrons. Okay, so now we know that it's 3d5, and we're trying to find what the quantum numbers that describe this are. So for quantum numbers, there are 4 different ones that we look at. There's the principal quantum number, n. There is the azimuthal angular quantum number, L. There is what defines our orbital, or m sub L. And then finally there is our magnetic spin, m sub S. We want to find all of these. So let's get to it. Our principal quantum number is the number that appears out front. So our highest energy is going to be our valence electrons here. We only have a 3D subshell. So all the core electrons are going to be lower energy than this. So our principal quantum number is going to be n equals 3. For L, remember we can do what I like to call the Adobe rule. And the Adobe rule is, if we look at the values of L, it can be 0, it can be 1, it can be 2, it can be 3. If we think about the letters that go with them, 0 is S, it's the simplest of these orbitals, and then it's like an Adobe file extension, .pdf. So since we're looking at a 3D subshell, that means that our azimuthal quantum number is going to be 2. M sub L. So m sub L can range anywhere from, so m sub L can go anywhere from negative L to positive L. So in this case, our options are negative 2, negative 1, 0, positive 1, positive 2. And it doesn't matter which of those it is. So like if we look at the last question that we did, same setup, it's the same valence shell here. Doesn't matter. We could fill this in, it doesn't have to go in that order. We could have filled in 1, and then negative 1, and then 2. Usually just by convention, just to make things easier, we start from the leftmost and then fill it in, but we don't have to do that. So it can be any of these values. Likewise, the m sub s, our magnetic spin, can be either positive 1/2 or negative 1/2. It doesn't matter which one we do, although whenever you're filling in a subshell, whichever one you put for the first orbital, it has to be equal to that for all the orbitals until you get them half-fulled, and then you can flip. Okay, so our m sub L can be any of these values, and our m sub S could be either of these. So if we look at these, which one of these works? The only one that matches is this one right here. E can't be right because, well, notice here that it says m sub L equals 3. That does not happen in a D subshell. We would have to go to an F subshell to make that happen. So in this problem, we're heating up some steel. All right. So it's helpful in a problem like this to create a heating curve. In our heating curve, what we're basically going to do is plot heat added on the x-axis and the temperature on the y-axis. So these are really useful because what they do is they give us a way of visualizing how much energy goes into or out of a system. And we're starting off at a solid. We're going to need to heat that solid up until we get to the melting point. At the melting point, we're going to add in heat, but the temperature is not going to change. This is an isothermic process. What's going on? It's melting. And then finally, we're going to add in heat, and we're going to make the liquid hotter. So, if we consider these different phases here, and these different parts of our curve, we have 3 steps. We're heating the solid, melting the solid, turning it into a liquid, and then finally we're heating the liquid. So this tells us that we're going to need to find the sum of 3 different steps. Step 1, step 2, and step 3. This is a great way for planning out our strategy. So all we need to do is find the energy associated with each of those, and we'll add them together to get the overall energy that needs to be added in. So step 1 is going to be heating our solid. In order to do that, what we're going to look at is our specific heat of solid steel. It tells us it takes 4.9 joules per mole Kelvin. So it takes 4.9 joules to heat each mole by 1 Kelvin. Okay. So technically we can use the equation here. Q, the amount of heat that we need to add, is equal to M times C, the specific heat or the molar heat capacity, times delta T, the change in temperature. But we don't actually need to use this equation if we just think about what's in our units here. It tells us the amount of energy we need to add for every mole, for every Kelvin. Okay, so what is the delta T? That we do need to figure out. And we're starting our steel at 500 degrees Celsius, and we're heating it until it gets to the melting point. So the melting point is going to be, we can see it's written on the side here, so it's 1,400 degrees Celsius is our melting point. Okay, so that means that our delta T for this first step is going to be, we're heating it up to 1,400 degrees Celsius, and we're starting at our initial temperature of 500 degrees Celsius. And remember, even though our units are in joules per mole Kelvin, with delta T, it doesn't matter if we use Kelvin or Celsius, because a change in Kelvin is equivalent to a change in Celsius. So our delta T ends up being 900 degrees Celsius, which is equal to 900 K. All right, now let's plug in and calculate. So here's our molar heat capacities, 0.49 joules for every mole Kelvin. And the number of moles that we have, well, it's 10 moles. So that'll allow moles to cancel out. And we're heating it by 900 Kelvin. So I should have said before, since we're given moles here, this is actually Q equals NC delta T, but both equations work, and it's all in the units. So let's see how many joules we end up getting from this process. So this ends up being 4,410 joules, which if we divide by 1,000, since all of our answers are in kilojoules, we might as well turn this into kilojoules as 4.41 kilojoules. Okay, step 1, done. But now we need to melt our steel. And melting is actually an easier calculation because with melting, the amount of heat you have to add in is just equal to the enthalpy of whatever process. In this case, for melting, it's fusion, times the number of moles you have. Or you could be given it in terms of the joules per gram, but here we're given joules per mole, so, or kilojoules per mole. So once again, as long as you keep in mind your units, you're going to be good to go with this. So our heat of fusion is 13.8 kilojoules per mole. So for every mole we have, it's going to take a cool 13.8 kilojoules. And we have a nice round 10 moles, which means that this step is going to take 138 kilojoules worth of heat. It's a non-trivial amount of heat. But after we do that, we're going to end up having our liquid. Step 2, ding, done. Finally, for step 3, it tells us that we want to heat up our liquid steel to 2,000 degrees Celsius in the problem. So that means that we're starting at 1400, we're going to 2000, which means that our delta T is going to be equal to 600 degrees Celsius, the 2000 minus the 1400. So once again, we're going to be using the Q equals NC delta T. Q is equal to, now we're going to be using the liquid heat capacity, which is 0.82 joules per mole Kelvin. So 0.82 joules per mole Kelvin. We have 10 moles that we're heating up. And we're heating it by 600 Kelvin. And we're going to get 4,920 joules, which again, to make that kilojoules, we'll just divide by 1,000 and get 4.92 kilojoules. Okay, so now to find the total energy, we need to add up this value, and this value to get the total energy it would take to go on our entire phase change adventure. So when we add them all up, we'll get our answer, which is 147.3 kilojoules. So the next time that you want to heat 10 moles of steel and melt it and get it up to 2,000 degrees Celsius, make sure to allocate about 147 kilojoules to do so. So this one, kind of a long process, but I hope what you saw from this problem is if we have a strategy, the actual algebra itself isn't bad. So once we have a plan in place, we can figure out how many steps are involved and we can find out the individual energy from each of those steps and we can get to our answer. In this problem, we're comparing bond angles. And notice that the lone pairs are not explicitly depicted, nor are the geometries. So I'm going to add in the lone pairs, make sure all of these things have octets, because that's going to be very important when determining our relative bond angles. So then, what we're going to do is we're going to consider the electron domain geometry of each of these different points, and we're going to rank them accordingly. So remember that the angles are dictated by two things, the electron domain geometry and how many lone pairs we have or double bonds to consolidate bond angles. So for instance, with this first one, we have 1, 2, 3, 4 electron domains. So the way that they can splay themselves out as far away from each other as possible is by making this tetrahedral shape, where everything is at a 109.5 degree angle from each other. But in this particular case, since we have two lone pairs of electrons, remember what the effect of lone pairs are. So let's say that we have a lone pair right up here, and let's say that we have a lone pair behind right here. What these lone pairs will do, they're wild, they're all over the place, they're not contained between two atoms. And so what they're actually going to do is push this angle in and consolidate it more than if we had 4 bonding pairs. So the more lone pairs we have, the smaller that actual bond angle is going to get. So ordinarily tetrahedral is a cool 109.5 degrees. Since there's 2 lone pairs, our angle is going to be less than that. And I'm going to put 2 less than signs. That'll become more evident why in just a moment. And that moment is, well, now. In this case, angle 2, we've got 4 electron domains, which means our base angle is 109.5. Now, wait a minute. How are we supposed to compare this to the first one if they have the same base angle? Well, now we only have this one lone pair of electrons. So I'm only going to put 1 less than sign here. And you don't need to know the exact angles. This one would probably be about 104, 105 degrees. And this one would probably be about 107 or so. But one lone pair is not going to be squished in as much as what would happen with 2 lone pairs. With bond 3, we've got 2 electron domains. And 2 electron domains can make themselves splayed out by being linear. So 180 degrees is as big as these angles can get. This one's going to be the largest. And then finally we have angle 4, which is just going to be our canonical 109.5 degrees. There are no lone pairs to consolidate our bond. So it's going to be the shortest is 1, then 2, then 4, and then our winner here is 3. 3 is the largest bond angle. So 1, 2, 4, 3. Okay, in this problem we need to figure out the formal charge on, we're looking at a glycine, and this glycine, amino acids are what are known as Witten ions. So what will often happen is the carboxylic acid will give up its proton, its H+, and the amine will gain an H+, and so we end up having this molecule here that ends up having 2 charges on it, 2 formal charges. So let's figure out what the formal charge is on each of these, and recall that the definition for formal charge is the number of valence electrons for a given element, aka its group number. And then from that, we're going to subtract the number of non-bonding electrons plus the number of bonds. Okay, so let's do this for number 1 first, and then we'll do it for number 2. So for number 1, nitrogen is in group 5, so its formal charge is going to be equal to 4 minus, 4, what am I doing? It's going to be equal to, it's in group 5, so it's got 5 valence electrons, minus, and on the structure, we have 0 non-bonding electrons, and we have, count them, 1, 2, 3, 4 bonds. So we end up getting that the formal charge will be equal to 5 minus 4, which is just equal to positive 1. Now we're going to do the same thing for oxygen. Oxygen is in group 6, and we're going to subtract the number of non-bonding electrons. So each lone pair is 2, 1, 2, 3, 4, 5, 6. And to that we need to add the number of bonds, which there's only 1 bond on this particular oxygen. So it's just going to be 6 plus 1, which ends up giving us a formal charge of negative 1. So the nitrogen is positive 1, and the oxygen is negative 1. This question, there's 2 different ways that we can go about doing it. If you're trying to find a constitutional isomer, you can never go wrong with finding the formula. Sometimes it takes a little bit longer to find the formula, but first I'm going to find the formula of this cyclohexene here. And on this molecule, we've got 1, 2, 3, 4, 5, 6 carbons. Okay, So it's going to be C6. And at this point, I could either count out the number of hydrogens, or I can use the fact that this has 1 degree of unsaturation by virtue of being a ring, and another degree of unsaturation by virtue of having the alkene here. And so that means each degree of unsaturation means 2 less hydrogens than the alkane counterpart would have. So the alkane version, the straight chain alkane of hexane, would be C6H14. This is C6H10. But don't take my word for it. Well, or do, but let's just show how we could also get this. We could annotate in our hydrogens if we wanted to. 1 here, there's 2 here, there's 2 here, there are 2 here, there are 2 here, and there's 1 here. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so our C6H10 holds up. Now then, to find which of these matches what we're trying to find, a constitutional isomer that has a trans conformation. So we could do this the quick way and look for 6 carbons with 2 degrees of unsaturation. If we're looking for 2 degrees of unsaturation, we can automatically eliminate this. That only has 1. It is C6H12. We can eliminate this. This one has 3 degrees of unsaturation. So this one's actually C6H8. Again, you can also always count the formula. You can do it the longer way, and that's a great way of checking your work if you have time. The last 3 all have 6 carbons and 2 degrees of unsaturation. So all 3 of these are C6H10. Alright, so now we're looking for the one that has a trans conformation. So the one that's going to have a trans conformation is, I'm going to draw an invisible line, not invisible because I'm drawing it, but I'm going to draw a line, rather, through my molecules, through the double bond that's parallel to, but going right through it. And if we have the same substituent on opposite sides, we're looking at trans. So here we have a hydrogen on that side, hydrogen on this side. They're on the opposite sides of the double bond. So this ends up having a trans conformation. Cool. If we look at this right here, this one is cis, because the hydrogens are on the same side. Up here it's neither, because there's a hydrogen on that side and a hydrogen on that side. So you have to have unique substituents coming off of each carbon in order for something to be cis or trans. So this one's just cis right there and neither up there. And if we look at this up here, this one actually, once again, is neither, because these methyl groups are the same thing and these carbons are the same thing. So, choice E. And our last question is, consider this Boltzmann distribution and which of the following are true. So when looking at a Boltzmann distribution, remember that for a given sample of gas at a given temperature, there's a whole array of different molecular speeds that you have. But the heavier gases are going to be skewed more toward lower speeds. So this is going to be the heaviest of these 3 gases. They're all at the same temperature. So this one's going to be the lightest right here, because it has the fastest distribution of speeds. Look at this. So this one has, it has some slow-moving ones on the left-hand side, but it's splayed out. It's got all these really, really fast-moving molecules over here. So anyway, now let's consider each of these statements and declare them true or false. So choice 1 says gas C has the greatest average kinetic energy. What are our thoughts on this one? I'll give you my thoughts. Bwah. Not true. So, average kinetic energy is only dependent on the temperature. Okay? So we're only interested in the temperature. Since these are all at the same temperature, these all have the same average kinetic energy, which means this is not true. They all have the same. 2 says gas A has the greater molar mass. So if we look at gas A, the greater the mass, the slower the gas. And indeed, this one's the heaviest. So I like that. I'm going to give that a big old check. Ding! The next one says gas C has the greatest RMS speed. If we compare the RMS speeds of each of these, so for A, we go slightly to the right of the highest point, we go down. So there's the RMS speed. It looks to be about 300 or so meters per second. For B, I probably should be using a line rather than trying to draw this myself. For B, it looks to be maybe about 700 or so. And then finally, for C has an RMS speed about 950. So C looks to have the greatest RMS speed, not just looks to, it does. And that's what this says, so indeed. And then it says that greater than 0.15% of the molecules of gas B are at the RMS speed. So to analyze that, let's look at the RMS speed for gas B. It can be found right here. And it says greater than 0.15%. Well, if we look where 0.15% is, nope. So I drew that line a little bit above where it's actually at. But we can see that B is clearly underneath that threshold. So this last one, we're going to put the kibosh on, which means that only 2 and 3 are true. So that concludes our video rendition of the annotated practice exam. For those taking the makeup exam, dominate! For those not, thank you for listening, and I hope that you have a wonderful rest of the day.